अभी एक गाना हमने सुना था हाल ही में कि मेरा यार हंस रहा है बारिश की जाए। सो ग्रेटर नोएडा का मौसम देख के लग रहा है किसी का यार बहुत खिलखिला के हंस रहा है। एनीवेज, क्योंकि कुछ ज्यादा ही बारिश हो रही है। एनीवेज, कमिंग डायरेक्टली टू द टॉपिक। सो टुडे वी आर गोइंग टू डिस्कस अ टॉपिक. I mean everyone, if you know mechanical, if you are from mechanical, आप पढ़ने में कितने भी तेज हों या कितने भी कमजोर हों, you must have heard about this stress strain curve. And this might come to your mind कि sir it is like so basic. We have already studied in class 12th. This stress strain curve, Hooke's law, elastic modulus, yield strength. So why it is required to study now? Because this is your basic. This is your fundamental. If you are dealing, see ultimately why we fabricate object? हम कोई भी चीज बनाते क्यों हैं? So that हम उसका प्रयोग कर सकें. और यदि हम उसका प्रयोग करेंगे, if we will use that object, obviously it will undergo through tensile forces, compressive forces. These kind of stresses will be exerted on that object. So you cannot make an object. You cannot make an object until and unless you are aware about its mechanical properties, until and unless you know stress strain curve. If you want to fabricate manufacturing engineering, production engineering, if you want to fabricate or manufacture a product, again you should know its mechanical properties. Then only you will decide ki how to fabricate it. Should I use casting? Should I use powder metallurgy? Which process should I use in order to fabricate my object? That depends upon the mechanical properties of the raw material. Again, there comes the role of stress strain curve. Okay, so this is like your basic. You know, until and unless you don't know A, B, C, D, forget about spelling Czechoslovakia. You can't even spell India. So this is your A, B, C, D. This is your base. So that's why we are going to study today stress strain curve. Now this will give you an example. We have moved from this era to this era. We have moved from era where the maximum speed of a vehicle used to be 30, 40, 50 kilometers per hour to today's era where the speed can go up to like 150, 200, 250 kilometers per hour. How that became possible? Due to miracle? No. Due to science, due to engineering, it became possible that we upgraded ourselves from this to this. One more example I will give you. If you see conventional cars, जो हम पुरानी पिक्चरों में देखते हैं, they used to look very bulky, very heavy. But you can see, and why? Because they were made of cast iron or steel. That earlier cars in 1940s, 50s, mostly they were made up of either cast iron or steel. But from 1975, there was an advancement. There was a change. The change was entry of aluminum. And you can see from 1975, exponentially the use of aluminum has increased. Right from 100, you can say, pounds per vehicle to 547, means almost 5.5 times the use of aluminum has increased when it comes to automobile industries. So how it became possible? How aluminum was able to substitute conventionally used material? That was made possible because we were able to evaluate its mechanical properties. We were able to say कि नहीं भाई, if we use aluminum, our vehicle performance will improve. Once we start using aluminum, गाड़ी का वजन घट जाएगा. गाड़ी का वजन घट जाएगा तो उसकी माइलेज बढ़ जाएगी. एंड माइलेज बढ़ जाएगी तो ना केवल फ्यूल कॉस्ट बचेगा आपका, फ्यूल सेविंग होगा, बल्कि also the harmful gases in the atmosphere, that will also be, you can constrain, restrict. I mean, if you reduce the weight of the vehicle by 10%, the fuel savings will be 5 to 7%. It is huge. पेट्रोल की कॉस्ट आप सबको पता है. You know, when it was 99, हम बहुत शोर मचा रहे थे. But now it is 100, 102, 104, 106. Who cares? I mean, we do care, but we are now habituated. आदत पड़ गई हमें. Now, increasing the weight of the vehicle by 100 kg, if, you know, weight saving. Why aluminum came into picture? Because The load carrying capacity was same, means not same in the sense it was beyond what was required, but at the same time we were able to save fuel. So increasing the weight of the vehicle by 10 kg will cause an increase in the fuel consumption by 6.5% and CO2 emission increases by 9.5 gram per kilometer. For every 1 kilometer, 9.5 gram of CO2 will be introduced into the atmosphere if you increase the weight of the vehicle by 100 kg. So आपको I hope थोड़ा बहुत समझ में आ रहा होगा कि how stress strain curve or how determining the mechanical properties has helped us in this automobile sector. This is just one of the examples. Now if you see, these are, this again shows that how mechanical properties are being utilized to get lighter vehicles. No men please, no men please, they are too heavy. I'm not saying this. If you see my weight, you can say that I'm the least qualified person to say this. No men please, they are too heavy. Low cost airline will only hire female cabin crew from now to save इकाई दहाई सैकड़ा हजार 10,000 लाख 3,30,000 euros a year on fuel, just by recruiting female in place of male as their cabin crew member. They are able to save this humongous amount of money every year. Why? Because females are assumed to be 33 to 44 pounds lighter than men. I mean, just because females are supposed to be lighter, women are supposed to be lighter, they are being recruited. And just by following that strategy, they are saving this humongous amount. इकाई दहाई सैकड़ा हजार 10,000 लाख 3,30,000 euros every year. And this is done by which company? Go Air. आप सबने सुना होगा Go Air flights. Now you can see what Mahindra and Mahindra, Maruti, BMW, Mercedes are doing for lighter, faster, cleaner and cheaper cars. This was published in Economic Times. So not only Indian companies, Mahindra and Mahindra, Maruti, in fact BMW or Mercedes are also concerned about this environment. They are also willing to make lighter vehicles. How are fastening methods being used to reduce weight in the automotive industry? Now, I focused in automobile industry, but that doesn't mean the uses is only restricted to automobile industry. Even in other industries also, you will find the application that how mechanical properties are being utilized in order to, make a better product, make better products. Now coming to next. Why I have given this example? Because whenever I teach you, I try to make you little bit familiar with research papers. So this is one of the research paper that was published by Jiang, and it was published in a very reputed journal called Carbon. So you can see that when the aluminum is pure, when we are using pure aluminum, then this is the nature of my stress strain curve. This is the nature of my stress strain curve. But when I added 0.5, just 0.5, 0.5 volume percent CNT, carbon nanotubes, you can see the curve shifted upwards. Yes, strength increases, but yes, ductility decreases. Strength increases, ductility decreases. Strength increases, ductility decreases. Again, when I increase the content to 2 volume percent, just 2 volume percent, the strength again increases, but the ductility again reduces. So you can say with the addition of carbon nanotube, there is a constant increase in strength, but there is also constant reduction in ductility. As I told you in my last class, life doesn't run on binary numbers, 0 or 1. CNT डाल दो, काम हो जाएगा. नहीं, जरूरी नहीं है काम होगा. Yes, strength बहुत बढ़ जाएगी, but ductility घट जाएगी. And this may lead to catastrophic failure. थोड़ा सा, suppose आपने कोई गाड़ी एल्यूमिनियम 5% CNT की बना ली. जरा समझिएगा. Suppose आपने कोई गाड़ी एल्यूमिनियम में 5 वॉल्यूम परसेंट CNT ऐड किया और बना ली उस गाड़ी को. सर इसका स्ट्रेंथ तो लाजवाब है सर. It will not be able to show any ductility. टक्कर लगा बच जाएगा, टक्कर लगा बच जाएगा, लेकिन थोड़ा और टक्कर लगा फिर वो खींचेगा नहीं, सीधा टूट जाएगा. यानी आपके अंदर स्ट्रेंथ होनी चाहिए, बट आपके अंदर डक्टिलिटी भी होनी चाहिए, नॉलेज होना चाहिए, लेकिन विनम्रता भी होनी चाहिए. नॉलेज हैज, यू कैन से नॉलेज इज सिनोनिमस टू स्ट्रेंथ एंड विनम्रता इज सिनोनिमस टू डक्टिलिटी। स्ट्रेंथ हो, डक्टिलिटी हो, नॉलेज हो, पर विनम्रता भी हो। हमेशा देयर आर एन नंबर ऑफ फैक्टर्स दैट कॉग्लोमरेट in order to form a product, in order to make a product, and this is just one of the examples. Now first I will give you example of UTM testing, how we find a stress strain curve. In this, whenever I say stress strain curve, it can be compressive curves also, but today we will be focusing more on tensile curve. So not a stress strain curve, you can say tensile stress strain curve, that will be more apt. Now you can see this is how we do tensile testing. First of all, we will make a sample that needs to be tested, and the sample looks somewhat like this, and this is just one of the examples. Mind it, all the samples will not look like this, but yes, mota moti you can say most of the samples, they look somewhat like this. This is like a dog bone shape. See, I did my test in Sharda University with, suppose, this dimension. So I said, this is my strength. Someone else in USA, UK, Mexico, London, anywhere, he did the test and he said that, sir, my sample is 150 megapascal. But उसको तो नहीं पता कि मेरा sample कैसा दिखता था. हो सकता है, it is a possibility that he would have used this kind of sample. तो ऑब्वियसली बात है, स्ट्रेंथ में डिफरेंस आ जाएगा. आप आई एम गिविंग यू टू आयरन रॉड्स, एक इतना पतला है और दूसरा इतना मोटा है. किसको तोड़ने में आसानी होगी? किसका स्ट्रेंथ कम होगा? जो पतला वाला है. सो हाउ दैट पर्सन सिटिंग इन लंडन विल नो कि लविश कुमार सिंह इन ग्रेटर नोएडा हैज यूज्ड द सैंपल ऑफ सो एंड सो डायमेंशंस. When I say 100 megapascal, it should correspond to a particular dimension, and that dimension is given by ASTM. यहां पर रोल आता है अमेरिकन सोसाइटी ऑफ टेस्टिंग एंड मटेरियल्स. यहां पर रोल आता है ASTM स्टैंडर्ड का. Whenever you make a sample, be it tensile sample, compressive sample, bending sample, shear sample, any kind of sample, it has to be as per ASTM standards. I will write in my paper that, sir, I have followed ASTM standard so and so. Then he will realize, okay, so and so standard follow किया है. So automatically he will come to know about the dimensions. कि अच्छा, ASTM standard so and so में लिखा था, the gauge length should be this much, the width should be this much, and thickness should be this much. So every time we have to mention the standard, the ASTM standard that we have followed. Why it is important? Because it brings uniformity in this research field. It brings it unifies the whole world. How it unifies? Again, I will give you one more example. I did compression test and this was my sample. And I said, sir, my compressive strength is 75 megapascal. I said only this. क्या काम चलेगा? नहीं. The person who is in Kolkata, the person who is in Mumbai, he will say, sir, this is aluminium. Sir, I have taken aluminium and this is my sample. Obviously बात है, इसका strength बहुत ज्यादा होगा. This strength will be somewhat like you can say 200 megapascal. So to remove this discrepancy, to remove this difference, we always make our samples as per ASTM standard. So I hope आपके दिमाग में थोड़ी थोड़ी बत्ती जली होगी कि why ASTM standards are important. Because they unifies the world through a common standard. ठीक है? Now, so first of all, we have to make the sample, and the tensile sample looks somewhat like this. Then that specimen is loaded somewhere over here. So this is your tensile sample. And then in the tensile sample, what we will do? Tensile. You know that what are different types of forces? If I say this is your sample, so if you pull it like this, somewhat like this, यदि आप खींच रहे हो, इट्स टेंसाइल। यदि आप इसको दबा रहे हो इसको, इट इज कंप्रेसिव। और यदि आप इसको ऐसे ऊपर से ऐसे रगड़ रहे हो और नीचे से ऐसे रगड़ रहे हो, आई रिपीट, सपोज दिस इज योर सैंपल, if I am applying a stress in this direction and from the bottom I am applying stress in this direction, इसको मतलब ऐसे ऐसे, then this is your shear component, shear stress. This is how you apply shear stress. So we are doing tensile test. So by default you can see tensile test बोले तो हम सैंपल को खींचेंगे. Now I'll tell you how to do that, how that test is done. So here what happens? So you will give a tensile stress. आप उसको खींचोगे, and how, with what force you will pull it, with what force you will give the tensile stress, that is determined by this load cell. Load cell determines कि किस स्ट्रेस से आप उसको खींच रहे हो. लोड सेल डिटरमाइंस कि किस स्ट्रेस से आप उसको खींच रहे हो. Then stiff frame and base. Obviously the frame has to be very strong, because if you would have done compression test, especially compression test, if your force is very high, suddenly sample टूटेगा और ठक से आके लगेगा. So if this frame is weak, it can crumble, it can get damaged. So your frame has to be very stiff and strong. Now obviously यहां से हम इसको ऊपर खींचेंगे, and here one thing is missing, that is called extensometer. I don't know, maybe it is missing from this image, but there is one term which is very important, extensometer. In stress strain curve, which I will show, you need to know the stress, कि हम कैसे खींच रहे हैं. With respect to stress, how my sample is deforming. With respect to stress, how my sample is elongating. So how will you calculate that elongation? How will you calculate that deformation? With the help of extensometer. This is the sample. Now I will apply tensile stress. मैं खींचूंगा इसको कस के, तो क्या होगा? ये धीरे धीरे पतला और लंबा होता जाएगा. Correct? Slowly, gradually, the diameter will reduce and the length will increase. I want that data. Sir, जब 1 megapascal प्रेशर था, तो मेरा जो लेंथ था वो 10 mm था, और जो मेरा डायमीटर था वो 2 mm था. Then I increased my stress. When the stress went to 2 MPa, then the length became 11 mm and the diameter became 1.9 mm. I applied more force. मैंने और ताकत लगाई. I make it like, suppose you can say 20 megapascal. Then my length became 15 mm and my diameter became 1.7 mm. So you have to monitor the change in dimension of your sample at every instant. You have to monitor the change in the dimension of your sample at every instant. And how to do that? With the help of extensometer. It will keep a track on how the dimension is changing with respect to your applied force. So I hope आपको थोड़ा बहुत चीजें समझ में आ गई होंगी. ये machine, specimen, ASTM, this load cell and that extensometer. Now engineering stress and engineering strain. Stress क्या होता है? Stress is nothing but force upon area. जिस force से आप खींच रहे हो. I am talking about suppose tensile stress. Stress is denoted by this symbol. Therefore stress is force upon area. थोड़ा सा ट्रिकी क्वेश्चन. सर which area? आप तो कह रहे हो कि diameter is constantly changing. So कौन सा area? When the area was corresponding to like 2 mm diameter, or when the area was corresponding to 1.7 mm diameter. किसके corresponding area हम consider करें? Stress continuously increasing, stress बढ़ रहा है, area घट रहा है. Here you can say F is the instantaneous load. F is the instantaneous load. And suppose my initial, this is like after 1 megapascal, my initial dimension was 9.9 mm length and 2.2 mm diameter. This was my initial condition. This was my initial condition. This was my initial condition. सो F इज द इंस्टेंटेनियस लोड, किसी भी मोमेंट पे जो लोड है, this is suppose when initially it was 1 megapascal the load, the force, then it became 2, then it became 20. So if I want to know the stress at 20, so my load will be considered corresponding to 20 megapascal. But in engineering stress, there is one more term which I will come later on. In engineering stress, the area will be the original cross section area. You will consider this load, you will consider this load, but every time the area will be corresponding to this, whatever was the initial area of your sample, वही एरिया आपका फाइनल माना जाएगा, सॉरी वही एरिया आपका स्ट्रेस कैलकुलेशन में कंसिडर किया जाएगा. सो इफ यू सी स्ट्रेस इज इक्वल टू फोर्स अपॉन एरिया, वेयर फोर्स यू कैन से इज द इंस्टेंटेनियस लोड, इंस्टेंटेनियस, but area is not area is not instantaneous, area is your initial, the first, शुरू में जो एरिया था वही एरिया मान्य होगा. सो आई होप आपको अब थोड़ी सी चीजें क्लियर हो रही होंगी. स्ट्रेस बोले तो फोर्स बाय एरिया, फोर्स खींचना, एरिया चेंज होगा, फोर्स विल बी इंस्टेंटेनियस. मुझे 10 सेकंड पे जानना है कि स्ट्रेस क्या है, सो 10 सेकंड पे जो लोड होगा वो कैलकुलेट होगा, लेकिन जो एरिया होगा वो शुरू का जो होगा वही कैलकुलेट होगा. Stress is equal to force by area, where F is the instantaneous load and area is the initial cross sectional area. Now the next is engineering strain. Strain is nothing but change in length upon original length. Change in length. थोड़ा सा see, I will say never by heart things. रटो मत, रटना तो है ही नहीं. Whenever you read anything, understand it, close the book, घूम फिर के आओ, दोस्तों से चैटिंग करके आओ, एंड देन सोचो कि जो मैंने पढ़ा था क्या मुझे वो याद है. अगर आपको याद रह गया तो आपको एग्जाम टाइम में भी याद रहेगा. यदि आपको याद नहीं रहा तो आपने रट्टा मारा है, आपको एग्जाम टाइम में भी नहीं रहेगा. सो अब इसको रटने की जरूरत है, चेंज इन लेंथ बाय ओरिजिनल लेंथ, चेंज इन लेंथ बाय ओरिजिनल लेंथ नहीं, विजुअलाइज करो. सपोज इनिशियल मेरा लेंथ है, मेरा जो सैंपल है, माई सैंपल हैज इनिशियल लेंथ ऑफ 10 mm. I kept on increasing the load, the length kept on increasing. So you can say after some time, when I want to calculate the stress, the length is 15 mm. खींच के 15 mm हो गया. So what is the change in length? Final length minus initial length, or you can say instantaneous length minus initial length. So net change क्या हो गया? Net change in length क्या हो गया? 5 mm. बोले तो 15 minus 10 mm, यही तो हो गया आपका ना, 5 mm divided by original length. Original. Many times this question will be asked that what is the difference between stress and pressure, and I'll be very honest, this question was asked in my interview at IIT Kharagpur when I went for PhD admission. When I went for PhD admission, this question was asked to me. Okay sir, you have Mr. Lavesh, you have worked on stress strain curve in my MTech also, then tell me what is stress. I said sir falana. Then okay, you are saying force by area na, because that's what we randomly say, instantaneously we say stress force by area. Then what is pressure? Force by area. अरे यार ये तो दोनों एक ही चीज है. But there is a difference. There is a difference, my friend, between stress and pressure. Stress क्या होता है? Is the magnitude of internal resisting force. When I say stress, it is internal resisting force. Internal resisting force. Pressure is the external force. So stress is the internal resisting force. मैंने इस डस्टर को कस के दबाया, I press this duster very hard. Then what will happen? This duster, its atomic structure, they will resist, because inside this duster also there is a distribution or an arrangement of atoms. They will resist कि नहीं हमको change नहीं होना है, I am already in my equilibrium state. So there will be internal resistance. and that resistance will be like stress, that resisting force will be like stress, और मैं जितनी ताकत से दबा रहा हूं that will be like pressure. Pressure is the external force. Then these are other differences. No device can measure stress directly. Stress, there is no device कि आपने उसको लगाया, okay, this is the stress. No. But pressure is a physical quantity that can definitely be measured by gauges or manometers. I think in your fluid mechanics lab or turbo machinery lab, you would have used this manometers. So stress cannot be measured, but pressure can be measured. Stress may be tensile, compressive and shear. So stress may be a tensile stress, a compressive stress or shear stress, but the pressure will always be compressive. Pressure will always be compressive, dabana, marna, compressive. ठीक है? The magnitude of stress at a point in different direction is different. The magnitude of the pressure at a point in all the direction remains the same. This is the point. So this point has some stress in this direction, sigma x, some stress in this direction, sigma y, and suppose some stress in this direction, sigma z. So sigma x may or may not be equal to sigma y, and this in turn will may be or may not be equal to sigma z. If they are equal, that's fine, but there is a possibility that they may not be equal. But when it comes to pressure, same thing. If you replace with pressure in x direction, pressure in y direction, and pressure in z direction. Pressure. So here pressure in s direction, pressure in y direction, and pressure in z direction will be equal. वो हमेशा equal रहेगा. ठीक है? So I hope आपको स्ट्रेस और प्रेशर में थोड़ा बहुत अंतर समझ में आ गया हो. You please go through the slides. I will share it with you all. Now this is your कहानी अब शुरू हो रही है. अभी तक क्या था? सिर्फ इंट्रो चल रहा था. Now let's come directly to the stress strain curve. So this is your stress strain curve. Y axis there will be stress and x axis there will be strain. This is a graph of you can say a normal crystalline material. Remember, this is a general representation. It is definitely not applicable to all the materials. Generally, a stress strain curve looks like this or somewhat similar to like this. But every material has this nature of curve? No. हर material का ऐसा curve होगा ऐसा कोई जरूरी नहीं है. Whenever it comes to a stress strain curve, you have to remember few points. The initial point, then elastic region, or you can say Young's modulus, then comes yield strength, then comes tensile strength, and then comes fracture point or fracture strength. So you have to remember these key points. तो आप कभी नहीं भूलेंगे. सबसे पहले 0, then I went through elastic region or Young's modulus, then I reached yield strength, then again I went ahead, I reached tensile strength, and then I reached fracture point or fracture strength. Now ये region होते क्या है? What is yield strength? What is tensile strength? What is fracture strength? What is Young's modulus? Now we'll see to that. So initially you see, in most of the sample, initially your stress and strain will increase like this. This is how your stress and strain will increase. First, आपने UTM में सैंपल लगा दिया, UTM मशीन चलाना शुरू किया. सबसे पहले मान लीजिए आपने थोड़ा सा स्ट्रेस लगाया, थोड़ा सा हमने सैंपल को खींचा, फिर छोड़ दिया, वापस इसी डायमेंशन में आ गया. खींचा, फिर छोड़ दिया. आई होप आप समझ रहे हो. इसको खींचा, फिर इसको छोड़ दिया. सो इट मींस इनिशियली योर सैंपल विल अंडरगो इलास्टिक डिफॉर्मेशन. इलास्टिक डिफॉर्मेशन बोले तो व्हेन यू अप्लाई द फोर्स द डायमेंशन विल चेंज, बट व्हेन यू रिलीज द फोर्स द डायमेंशन विल कम बैक टू द इनिशियल वैल्यूज. यानी इसका डायमेंशन बदलेगा, लेकिन जब आप छोड़ दोगे तो वापस वो उसी डायमेंशन में आ जाएगा. डायमेंशन चेंज होगा, छोड़ दोगे वापस उसी डायमेंशन में आ जाएगा. सो दिस इज योर इनिशियल रीजन. This is your elastic region. In elastic region, when the force is subsequently removed, the body assumes the dimensions it had prior to the application of force. आपने फोर्स लगाया शुरू में, पहला मैं आपको इसके बारे में बता रहा हूं. ये जो कर्व है, शुरू में आपने फोर्स लगाया, खिंच गया, आपने छोड़ दिया, वापस आ गया. So suppose if I say my elastic region is up to here. If I say my elastic region is up to this point, so this is my stress. This stress is suppose 80 megapascal. My elastic region is up to 80 megapascal. So if I apply 70 megapascal stress, it will change in dimension. It will come back to the original dimension. If I apply 60 megapascal stress, it will change the dimension. Once I remove the force, release the force, it will come back to the original dimension. So up in this elastic region, there will always be elastic deformation. So this is your elastic deformation and this is your first region. Second, इस region की जो खूबी है, the second beauty is that stress is directly proportional to strain. Stress and strain will always be proportional. Proportional. जितना ताकत लगाओगे, सैंपल उतना डिफॉर्म होगा. कम ताकत लगाओगे, कम डिफॉर्म होगा. We can say that they are always proportional. Stress and stress is always proportional. And now the beauty comes. This proportionality constant can be removed by introducing a constant called E. When I'm saying stress and strain are always proportional. So if I divide stress by strain, it should give a number because they're always proportional and that number will always be constant. So whenever you divide the stress by strain, it will give a fixed number. Whenever you divide stress by strain in this region, it will give you a fixed number for a particular sample and that fixed number is called elastic modulus. बचपन से पढ़ते आ रहे हो इलास्टिक मॉडुलस. अब इलास्टिक मॉडुलस क्या होता है? स्ट्रेस बाय स्ट्रेन. ये तो समझ में आ गया. स्ट्रेस बाय स्ट्रेन विल बी इलास्टिक मॉडुलस and elastic modulus will always be applicable in this region and this principle is called Hooke's law. Hooke साहब ने पता लगाया था एक्सपेरिमेंट करने के बाद कि in this region stress is always proportional to strain and the ratio of stress by strain. Now remember, visualize. If you divide the stress by strain, it will give you the value of elastic modulus E. If you divide stress by strain, again E. Stress by strain. So basically the slope of this curve will always give you elastic modulus. Elastic modulus is nothing but the slope of stress strain curve in the elastic region. Because you can see, yahan tak to slope same lag raha hai, but now here the slope is changing. So elastic region or Hooke's law is only valid in the elastic region. So पहला समझ में आ गया. Elastic region, प्रेशर लगाया, सैंपल डिफॉर्म हुआ. प्रेशर छोड़ दिया, सैंपल ओरिजिनल डायमेंशन में आ गया. And in this region, stress is always proportional to strain. And in this region, elastic modulus we can find out in this region. ठीक है? Elastic modulus is nothing but the ratio of stress by strain, or you can say the slope of this curve. Now, in some books you will find कि elastic region भी दो हिस्सों में बटा रहता है. In every book you will not find, I am telling you. In every book you will not find. After elastic region you will directly find yield strength. But there are several books that writes कि elastic region भी दो हिस्सों में बटा रहता है. एक जिसमें Hooke's law valid है, एक जिसमें Hooke's law valid नहीं है. Elastic region is also divided into two regions. One region in which the Hooke's law is valid and in one region where the Hooke's law is not valid. So it is a possibility that up to this point, see, this is like yield strength. So beyond this everything is elastic, everything is elastic, everything is elastic. So maybe up to this point Hooke's law is valid. Hooke's law is valid matlab elastic deformation is there and stress is proportional to strain. But in this region, it is a possibility that elastic deformation is there, but stress may not be proportional to strain. So there are two schools of thoughts. But up to this point, elastic deformation or elastic region will be there. And one beauty of elastic region is that what I was telling you initially, this is your stress, this is your strain. Now if you apply stress, the strain will increase. And this is your elastic region. Up to here you have your elastic region. When you remove, you applied stress up to here, up to this point, and then you release the stress. So what will happen? It will trace back to the original path. It will regain the original dimension. So this way it will deform and once you release the force, reduce, or you can say once you release the force, it will come back to the original dimension. It will trace the same path. So this is your case in the elastic region. Now let's move ahead. So basically, elastic modulus, what is elastic modulus? An elastic modulus is a quantity that measures an object or substance resistance to being deformed elastically. Elastic modulus is nothing but the slope of the stress strain curve. The slope of the stress strain curve. It means if the slope of the stress strain curve, if the slope is high, value is high. Slope is low, value is low. Slope is high, value is high. Slope is low, value is low. So slope high, elastic modulus high. Slope low, elastic modulus low. The value of elastic modulus is low. ठीक है? Actually, I'll be very honest, why I'm emphasizing so much on this, in this concept, is because in every exam, in your viva, in your interviews, you'll be asked this question. Sir, what is elastic modulus? Sir, what is yield strength? Sir, what is tensile strength? Sir, what is fracture strength? Sir, what is hardness? What is resilience? What is toughness? What is ductility? Sir, सब तो एक ही जैसा लग रहा है. Yield strength, tensile strength, fracture strength, toughness, ductility, resilience, सब तो मोटा मोटी एक जैसा लग रहा है. But no, there are two materials. One material has A material, very high elastic modulus, and the other material B has very low elastic modulus. And your elastic modulus is nothing but stress by strain. So when I say elastic modulus is very high, it means sigma value is very high, which means strain value is very low. When I say this value is very low, this value is decreasing, this value is very low, it means sigma is also low and strain is very high. आप इसको मानो बोली, इसको भी मत याद रखो, कंसेप्ट के लिए आप समझो. When the elastic modulus is very high, the deformation, the strain will be very low. नहीं साहब मैं इस जगह पे रहूंगा, मैं नहीं हिलूंगा. When the elastic modulus value is very low, the strain will be very high. तुरंत यहां से मैं यहां आ जाऊंगा. So it means here the material will show a lot of resistance to elastic deformation. Why elastic deformation? Because इसकी applicability ही elastic region में होती है. So resistance to elastic deformation is symbolized, can be calculated by the magnitude of Young's modulus. सर इसका एप्लीकेशन क्या है? इसका एप्लीकेशन उन जगहों पर है where strength, बहुत ज्यादा ताकत की आवश्यकता नहीं है, लेकिन योर इलास्टिक प्रॉपर्टी शुड बी गुड, इजिली डिफॉर्म हो जाना चाहिए. एग्जाम्पल साइकिल, मैं आपको बाकी सब छोड़ो. साइकिल में भी जो हम रॉड लगाते हैं, मान लीजिए हम साइकिल चलाते हैं, आप साइकिल में आगे देखिए पुराने जमाने की जो साइकिल होती थी वहां रॉड लगी होती थी. उस रॉड पे यदि बच्चा बैठेगा तो वो रॉड ऐसे झुक नहीं जाना चाहिए. दैट रॉड शुड बी स्ट्रेच, इट शुड बी स्टिफ. इलास्टिक मॉडुलस स्टिफनेस, स्टिफ, दैट रॉड शुड बी स्टिफ. इफ द स्टिफनेस इज लो, इफ द इलास्टिक मॉडुलस इज लो, बच्चा उसके ऊपर बैठेगा और वो ऐसे बेंड हो जाएगा, वो ऐसे कर्व हो जाएगा. बॉडी इंप्लांट्स, बॉडी इंप्लांट्स, जैसे मान लीजिए लोगों के घुटने टूट गए या फिर मान लीजिए यहां पर कोई हड्डी टूट गई तो वहां पर हम एक इंप्लांट लगा देते हैं, बायो इंप्लांट. आई मीन आप सब इसके बारे में जानते होंगे. सो ऑब्वियसली बात है, इफ आई एम कीपिंग एन इम्प्लांट हियर, इफ आई एम इम्प्लांटिंग एन इम्प्लांट हियर, so that implant will obviously be able to resist my force, जो मेरा वजन है, my weight. But थोड़ा सा वजन पड़ा और यदि वो इम्प्लांट टेढ़ा हो गया तो आपका यहां दर्द शुरू हो जाएगा. That implant should be able to resist your, the initial deformation that you give. उसकी इलास्टिक मॉडुलस अच्छी होनी चाहिए, स्टिफनेस अच्छी होनी चाहिए. Conventional materials are there. In general, the elastic modulus of polymers or forms are assumed to be least. And then comes metals and then comes ceramics. So ceramics, they have highest elastic modulus. Example, जो बेसिन आप घर में यूज करते हैं, जो बेसिन जिसमें आप मुंह धोते हैं, जो बेसिन आप यूज करते हैं सेरामिक्स का, या फिर जो कमोड आप यूज करते हैं, वो सारी चीजें जो है सेरामिक्स की बनी होती हैं. यानी उस पर यदि आप बैठ जाइए, उस पर यदि आप कूद भी लीजिए, वो डिफॉर्म नहीं होगा. भले टूट जाए लेकिन डिफॉर्म नहीं होगा, सीधा टूट जाएगा लेकिन डिफॉर्म नहीं होगा, टेढ़ा मेढ़ा नहीं हो जाएगा. कि सपोज कमोड इज देयर, एक 80, 90, 100, 150 किलो का आदमी बैठा और हमारा कमोड जो है ऐसे टेढ़ा हो गया, ऐसा नहीं होगा. सो देयरफॉर सेरामिक्स हैव द हाईएस्ट वैल्यू ऑफ इलास्टिक मॉडुलस. नाउ कमिंग टू नेक्स्ट, this I have already explained. Now here one more thing I would like to emphasize कि ये कर्व मैंने आपको ऑलरेडी बता दिया है. But if you see this curve, why this curve is important? Because see, sir, you see that the curve will be initially like this. Initially it will be a straight curve, a straight line, but it may or may not be possible. There are certain cases like cast iron, gray cast iron or concrete, whatever you say, few examples are mentioned. In that case, the curve is somewhat like this. Curve is somewhat like this. It's not straight, it's somewhat bent. It's somewhat bent. So this is your curve. Now how to find the elastic modulus? Because here, whether you calculate the slope at this point, this point, this point or this point, the slope value will be same. But here, if you calculate the slope at this point, this point, this point or this point, at every point, the slope will be different. So it means your material will have so many values of elastic modulus, which is not possible. ऐसा नहीं होता है. Any material at a particular instant will have only one value of elastic modulus. So now the next question comes कि सर फिर आप तो कह रहे हो यहाँ पे at every point the elastic modulus value will be different. I mean the slope will be different. So how to calculate the elastic modulus in case when the curve is like this? So there are two commonly used practices. We choose, one is like this tangent modulus. In tangent modulus what we do, we choose a stress, and at this stress point whatever is the value of slope, that will be your elastic modulus. Doesn't matter what is value here, doesn't matter what is value here, there will be a predetermined stress sigma 2, sigma 2, sigma 2. Whatever is the value of slope, whatever is the value of slope at this point, sigma 2 point, that will be your elastic modulus. Done and dusted. The second case could be you can choose a point sigma 1. You can choose a point sigma 1, but you will not calculate the slope at this point. In second case, you will join this point with the initial point. You will join this point with the initial point, and iska jo curve hoga, that will be your elastic modulus. And this is known as secant modulus. This is known as tangent modulus. This is known as secant modulus. So in case of tangent modulus, what we do? We choose a predetermined stress. Corresponding to that stress, whatever is the slope, that is my elastic modulus. In secant modulus, what we do? We choose a stress, predetermined stress, and then we join that with the initial point. Join that with the 0 point. And us line ka jo slope hoga, that is your secant modulus, or that will be your elastic modulus. So this is all about tangent modulus and secant modulus. Now next comes plastic deformation. चलिए ये elastic region आ गया. Now we are entering into the plastic region. Now we are entering into the plastic region. Now in what is plastic region? What is a plastic deformation? Initially elastic deformation होगा, but after certain level of stress, if you exceed that level, the deformation will be plastic. Plastic deformation means when you release the stress, if you exceed certain limit of stress, and if you release that stress, the dimension will not come back to the original dimension. There will be some permanent change left in your sample. There will be some permanent change in your sample, and that will be by virtue of plastic deformation. In case of elastic deformation, if you release the stress, it will come back to the original dimension. In case of plastic deformation, if you release the stress, it will not come back to the original dimension. कुछ न कुछ उसमें deformation रह जाएगा. So the moment you enter this region, elastic region, the moment you enter in this plastic region, then comes this yield strength. Now plastic deformation is clear. Now the gateway or the wall between elastic and plastic region is the yield strength. Yield strength is your gateway to the plastic region. So yield strength क्या होता है? Now this point is yield strength. Yield strength बोले तो the minimum stress, the minimum कम से कम, the minimum stress that is required in order to have plastic deformation. Yield strength is the material property defined as the stress at which a material begins to deform plastically. उस point पे, at this point, the material will start to deform plastically. इस point के बाद अब elastic deformation नहीं होगा, अब plastic deformation होगा. इस point के बाद खेला होबे, अब plastic deformation होगा, अब elastic deformation नहीं होगा. आप लोगों ने इलेक्शन सभी देखे होंगे तो उसमें बहुत एक कॉमन वर्ड था खेला होबे. सो इस पॉइंट के बाद खेला होबे, देयर विल ओनली बी प्लास्टिक डिफॉर्मेशन. इस पॉइंट के बाद देयर विल नॉट बी एनी इलास्टिक डिफॉर्मेशन. सो यील्ड स्ट्रेंथ क्या होता है? एग्जाम में पूछा जाता है यील्ड स्ट्रेंथ क्या होता है? इट इज द स्ट्रेस. यील्ड स्ट्रेंथ इज करस्पॉन्डिंग टू द स्ट्रेस. यील्ड स्ट्रेंथ इज करस्पॉन्डिंग टू द स्ट्रेस एट विच a material begins to deform plastically. उस पॉइंट के बाद से प्लास्टिक डिफॉर्मेशन का प्रारंभ होता है. So that is your yield strength. The magnitude of the yield strength of a metal is measured by its resistance to plastic deformation. Yield strength ज्यादा होगा मतलब प्लास्टिक डिफॉर्मेशन करने के लिए ज्यादा स्ट्रेस लगाना पड़ेगा. Yield strength कम होगा मतलब थोड़ा सा स्ट्रेस लगाया प्लास्टिक डिफॉर्मेशन शुरू हो गया. मतलब yield strength ज्यादा प्लास्टिक डिफॉर्मेशन करना मुश्किल, यील्ड स्ट्रेंथ कम प्लास्टिक डिफॉर्मेशन करना आसान. सो यील्ड स्ट्रेंथ इज नथिंग बट इट मेजर्स द रेजिस्टेंस ऑफ द मटेरियल टू प्लास्टिक डिफॉर्मेशन. आई होप आपको ये चीज समझ में आ गई हो. नाउ लेट मी सी हाउ मच टाइम इज लेफ्ट. ओनली 1 minute इज लेफ्ट. सो नो प्रॉब्लम. आई थिंक आई विल रैप इट over here. We'll continue in the next class.